Good afternoon. It is Friday, November 8th at 3:33 p.m., and these are the Tobin Time Travel Talks. Today, we're going to talk about quantum mechanics.
There was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics.
That was Nobel laureate Richard Feynman telling you about how completely incomprehensible today's subject is. So that should tell you about how rough covering quantum mechanics is going to be. You see, we had a saying about quantum mechanics back in college. I hate quantum mechanics and I wish it would go away. See, if you polled every physics major out there, they'd tell you their number one least favorite class was statistical mechanics, which, to be fair, stat mech is just the worst. It is way worser than quantum mechanics. But if you asked all the engineering majors who had to take quantum and didn't have to take statistical mechanics, which physics class was the worst, all the engineers would tell you that quantum's the worst. Where was I going with this? So given how awful it is, why do we tolerate quantum mechanics? Well, despite how complex it is, it's accurate. It's our most accurate way of describing subatomic processes. Speaking of which, what is quantum mechanics? So quantum mechanics is used to describe small things. Things like electrons, photons, gluons, leptons, quarks, positrons, and other fun stuff. I'd seriously considered making up funny words to describe more subatomic particles, but a lot of them already have really funny names, like neutralino, snootrino, and inflaton. Anyways, in addition to describing subatomic processes by virtue of averages, quantum mechanics is also an extraordinarily complicated way of describing normal-sized things, like arms and televisions. So what's with all this quantum bashing, you might say? Why does everyone hate it? Quantum mechanics is what happens when physicists want to be mathematicians. So in normal physics, i.e. classical mechanics, you got this conservation of energy equation, for example. Maybe an object is in ballistic motion, so it has a kinetic energy of 1/2 mv squared and a potential energy of mgh. So its ballistic trajectory will look something like this. Simple and pretty. But quantum. In quantum mechanics, you got this ridiculous Schrodinger equation that's the basis for everything. Instead of these particles having a trajectory like a normal person, they use these wave functions to describe them. And in the absolute simplest case, where we toss a particle in an infinitely deep well, that wave function is a sine wave. So with this wave function, you can't actually get the position and the velocity of the particle anymore because of statistical uncertainty. You have to slap an operator on that equation, and it'll give you a probability function that describes the position. And by operator, I mean you slap a hat on top of this letter, and you call it an operator, and now it's a function of a function. And we don't use velocity anymore, we primarily use momentum. So in regular physics, momentum is just the mass times the velocity. But in quantum, momentum is the spatial derivative multiplied by h bar, and then we also add in the imaginary number I. And that makes the whole Schrodinger equation look like this mess. And if we slap that momentum operator onto our wave function to find out what the momentum of this particle is, that just spits out a cosine function that gives us a distribution of possible momentum states. It's a slog. But breathe easy. We're not going to be talking about all that mathematical nonsense today. There are a few core principles to quantum mechanics, things like wave functions, discrete energy values, those stupid operators, and that whole wave-particle duality thing you might have heard about. But what's relevant today is this: randomness. Not the unpredictable but deterministic dynamics of chaos. Not pratfall! No. True randomness. The absolute impossibility under any circumstances of predicting the outcome of a situation. Now, when we think about random numbers, we might think about something like a die. Rolling a 6-sided die that is well weighted has a relatively even chance of landing on any one of its 6 sides. That's random, right? Well, the thing is, if you take into account my rolling technique, the angle of the surface I'm rolling on, the starting position of the die itself, the air pressure, all that stuff, you can calculate the exact result that this is going to roll every single time. The only randomness comes in our inability to measure and calculate those with absolute certainty. Case in point, I knew I was going to roll a 4. That's not the randomness of quantum mechanics. Things like location, momentum, how long it takes for an atomic nucleus to decay. It doesn't matter how good our instruments or our calculations get. There is no way to escape the physical limit to how precisely these can be measured, calculated, and predicted. For example, if you fire an electron at a wall of atoms, there's a finite, non-zero probability that it will bounce off the wall. And there's also a finite, non-zero probability that it'll appear on the other side of the wall without having disturbed the wall at all. This is part of that wave-particle duality thing. And there's no way to predict with certainty whether it'll bounce or whether it will tunnel. You just have to fire it and see what happens. So, unlike chaos, there's not really an example of quantum randomness that we can apply on a scale that is intuitive to us, because quantum mechanical processes inherently happen on an unintuitive scale. So, like, if we tried to press our bodies against a wall to see if they would tunnel, the wave functions of the octillions of atoms in our body would all collapse into what is essentially a deterministic chaotic whole. There's technically a possibility you could tunnel through that wall, but it's about 1 in, like, Google. That's 1 followed by 100 zeros. Basically, once you get to human scales, quantum mechanics collapses into chaos. Alright, so after all that, you're probably wondering why I'm talking about this in a video series about time travel. Well, it goes back to the idea that if the outcome of a process is random, how does the universe decide whether that electron tunnels or bounces? Which will it do? And why? There are several interpretations of what quantum mechanics means in this regard, each with their own little explanation about it. The most common is the Copenhagen interpretation, which basically is what you see is what you get. Everything's random and meaningless, just deal with it. Not helpful for our purposes. Boo, Copenhagen interpretation. Now, the far superior interpretation, with respect to time travel, is the many worlds interpretation. According to the many worlds interpretation of quantum mechanics, the universe doesn't decide whether one thing happens or the other happens. The universe just splits into 2 universes, one of which where one thing happens and one where the other happens. Universe A, the electron bounces. Universe B, the electron tunnels. So every time we have a quantum mechanical interaction, we make and enter parallel universes. And since basically every particle in the universe undergoes some kind of quantum mechanical interaction constantly, the universe is constantly splitting. And that results in a staggering number of universes. Now, if you're a little nerdling like I was, you're going to look at this and say, now wait just a proton slapping second here. If energy can't be created or destroyed, then how can you create a whole new universe every time some quantum mechanical interaction happens? The universe has 10 to the 71st joules of energy in it. So when you create a new universe, you create 10 to the 71st power joules out of nothing. Well, the trick that physicists made up to explain this is that on a multiversal scale, it's not a single universe's energy that's conserved. Instead, it's some quantity that's shared and conserved across the multiverse. Last time I looked it up, it didn't have a name, so I'm going to call it the multiversal hyperenergy. So when you multiply the energy in a universe by the probability of that universe existing, then add all the universe's energy probabilities together, you get this constant hyperenergy. We're just going to have to accept that. What if we're looking at a measurement that's not discrete? Instead of looking at whether it bounces or doesn't, a binary decision, what if we're looking at exactly how much time it takes for a uranium atom to decay? Since it could happen at X nanoseconds, Y nanoseconds, Z nanoseconds, 80 years, anywhere along that spectrum, instead of splitting into two universes, it splits into several. In fact, we're really splitting it into an infinite continuum of universes. And so, with all that, we have a real-world scientific basis for the concept of alternate universes. This is going to inform a lot of our analysis going forward when we talk about branching timelines. Of course, we don't have a way to go between these different universes. In fact, we can't prove they exist in the real world. That's what makes it an interpretation of quantum mechanics. And we can't really control anything about that splitting. But it is an actual scientific theory with a lot of mathematics to back it up. And we're going to have to hash out a lot of details about it in the future, but I think we can leave off here for today. As always, if you want to read the nerdiest book ever written, the Chronoversal Compendium is available on Amazon, or you can get a special discount on the hardcover with the Ingram Spark link in the description. That's all for now. See you yesterday.